All right, so we have just 2 examples left to go. So let's get back to that and see if we can finish this up. B, this series from n equals 1 to infinity of n factorial over 2n factorial plus 1. Okay, so what can we do for this one? Well, I'm going to try the nth term test and see what happens. So I'm going to take the limit as n approaches infinity of this nth term, n factorial, divided by 2n factorial plus 1. And I can't use L'Hopital's rule, by the way, because I can't take the derivative of a factorial. It's just not one of those things that's a function, a continuous function, that has a derivative. So we're going to have to think of an algebraic trick to make this work. One of the things I say in my pre-cal class and early calculus class is, if it's polynomial, we're going to use a trick here of find the highest power of n in the denominator and use its reciprocal over itself as a form of 1 to algebraically trick it into being able to find it. So I'm going to use that same idea. I've got n factorial in both places. So I'm going to multiply by this form of 1 over n factorial divided by nice little algebraic trick. And when we do that, n factorial times 1 over n factorial is 1. 2n factorial times 1 over n factorial, and distributing gives us 2, plus 1 times 1 over n factorial gives me that. Now as n goes to infinity, n factorial grows really rapidly. It goes to infinity, and the constant 1 over that infinitely large thing is headed towards 0. The limit of each of those constants is that constant, and this ends up being 1/2. Well, why did we do all that? Well, this is the nth term test, that we did the limit as n approaches infinity of our general term for the series, and what are we going to compare it to for the nth term test? Well, is it equal to 0 or not? If it's equal to 0, the nth term test is inconclusive and you need to try something else. And so all of this I've written down wouldn't have been any help. But when it is something that's not 0, we can automatically, after saying that answer, which you will have to find the correct answer for that, like here 1/2, and then claim that it's not equal to 0, and then we can make the claim about the series convergence. This series of n factorial over 2n factorial plus 1 diverges by, and now you have to always give me the name of the test you're using. So this is by the, oops, got ahead of myself, by the nth term test, nth term test. You can write for divergence if you want to. That's the full name of this test, but I'll let you get by with just writing the nth term test. That'll be sufficient. Okay, one last example. Example C. Right, so this series that we're given is from n equals 1 to infinity, 1 over n. So I want to write out a few terms of this one. 1 over 1 is 1. 1 over 2 is 2. 1 over 3 is 3. Plus 1/4, etc. This is actually a named series. There aren't that many of them. This is one of them. This is called the harmonic series. And whenever we find out stuff about the harmonic series in a section later on. We're going to find out if it's always convergent or always divergent. This series is one of those two. And after we prove whether it's convergent or divergent always, then whenever you need it, you can just say it's the harmonic series, therefore it diverges, or therefore it converges. So anyway, if I try to do the nth term test, take the limit as n approaches infinity of that nth term, that general term, 1 divided by an infinitely large thing is headed towards 0. Equals 0 tells us nothing. So the nth term test, and you won't have to write this much because you'll just do this in your head. The nth term test, when you get equals 0, is inconclusive. So if you're told to use the nth term test and you get 0, you will have to write this. But generally speaking, that's not a thing. If the limit is 0, then you're going to go about trying to figure out, well, actually, does it converge or diverge? Because that test doesn't tell you anything. If it's something that's not 0, you can go straight to divergence and you're done. So anyway, right now we can't draw any conclusions about this one. I'm going to give this one away right now because I told you earlier that you're going to see this. Here is a limit of a sub n that is actually equal to 0. The harmonic series always diverges. It's a divergent series. So just because we got equal 0 doesn't mean that it converges. Just because I'm a male doesn't mean I'm on the Dallas Cowboys team. So this 0 is inconclusive. We don't know if it'll converge or diverge at this stage. Later on we'll prove that this one diverges always. Anyway, that's the end of this section, the end of 9.2. I will see you in class.